Thank you for a wonderful morning. It was great, the speakers that we had and your interactions with them were wonderful. I'd also like to thank Gordon Campy. You may have seen Gordon with his camera. So we will have a record also of our symposium through Gordon's fabulous pictures, as many of us know about. Okay. So it's my pleasure to introduce our luncheon speaker. Our luncheon speaker is Dr. Lesley Fellows, and her fundamental research involves studying the effects of focal frontal lobe injuries or neurochemical changes like the kinds you would get in Parkinson's disease. She's also involved in clinical research aiming to improve how we diagnose and treat mild cognitive changes and mental health symptoms. She's involved also in McGill's Healthy Brains for Healthy Lives initiative. And that initiative aims to better understand how the brain changes across the lifespan. We're perfect candidates for her study. And in response, of course, to illnesses and other stressors, like what makes some people more vulnerable and some more resilient in the face of such challenges. The hope is that this knowledge will basically improve how we prevent, diagnose, and treat brain disorders. In addition to everything else she does, she leads the Cognitive Neuroscience Research Group at the Montreal Neurological Institute and is the Assistant Dean Academic Affairs in the Faculty of Medicine. So we are going to hear her speak about this older, wiser, and still learning, very interesting topic.
Thanks very much. And thank you for inviting me. It's been a great session so far. I congratulate the organizing committee. This is a lot of work to put together this kind of meeting. And I'm honored to be involved. And the title just refers to me. So far this morning. Okay, 3 hours older, definitely wiser. All right, so the luncheon slot is that's a tough. I've spoken on a few occasions to sort of older McGill crowds of one kind or another. As I was saying to my companion at the table there, I work with older people as a neurologist. I have. I'm interested in public outreach and have done some work for McGill in terms of speaking to alumni and so on. And then, of course, as a department member or someone playing an administrative role in the faculty, I work with lots of older people, for better or for worse. They're not always in a good mood. But anyway, I thought I would try to keep you awake while you digest your lunch as my first goal, and then touch on these four kind of topics briefly. Without knowing exactly what your own agenda is, I was planning to touch on them and hopefully leave enough time that you can ask me questions on whichever parts you find most pertinent. So I'm going to talk a bit about the neuroscience of learning, how the brain learns, what that even means, and hopefully maybe broaden your perspective on what we mean by learning in the brain. And then I'll speak briefly about the effects of age, late life aging on the brain. And then I'm going to talk about how to look after your brain, long-term and short-term. And you'll see maybe at that point that I'm going to sound less and less like a neurologist or a neuroscientist and more like a champion of social justice, because I really think a lot of the issues actually this morning in relation to societal, let's say, structures and marginalization and inclusion are maybe more important than a lot of the things that neuroscientists spend more time working on. Hopefully my colleagues are not watching this on the live stream. Okay, so first of all, let's talk about learning in the brain. So one question we could ask is why does the brain learn? And one of the things about neurobiology or biology in general is there should usually be a reason for any biological system that typically we think of from an evolutionary point of view is how does this system make the organism more fitter, more likely to survive from an evolutionary point of view. And when we think about learning, usually in the same breath we say learning and memory. Having learned something, there we remember it, kind of by definition. Memory, people usually think about it in terms of the past. That's what you're remembering is the past. But from an adaptive point of view, the reason, I would say, that the brain remembers is not about the past, it's about the future. So information about the past is only pertinent to survival if it's going to help you predict the future. And that's the main purpose of learning in the brain. I'll make that claim. And the brain's main job is to predict. It doesn't matter, the past is over. It doesn't matter what happened in the past. It's what's about to happen next. So the past is informative about what's about to happen next. That's why we are helped if we remember it. So that, in a nutshell, is, you can think about that from second to second. You can think about that over an entire lifespan or across a society, across generations. That basically our ability to predict what's coming next is what allows us to be more likely to survive. So the brain is a prediction machine in a very profound way, not only in thinking about all the luncheon speakers you've ever heard and what is likely to be like this time. You have some sense, probably. But also from second to second, what you're even experiencing in the world around you is related entirely or substantially to prediction. We have the kind of illusion that we process in detail everything around us, but in fact the sensory systems in the brain are kind of getting a rough idea of what's going on, and then just assuming things are going to continue that way until further notice, and updating when they don't, because it's predicting. The speaker is going to stand there and keep talking, blah, 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 and suddenly if I sort of walk off, you're going to pay more attention and process in more detail because that was not expected. So that kind of basic prediction is at the core of how the brain works in general. And a really fundamental principle of learning is that actually comes or is influenced to some degree in the thinking in computer science and machine learning and the artificial intelligence we were hearing about a little bit this morning. But that has also been influenced by neuroscience principles studying basic aspects of learning, is that learning is basically what happens when the predicted outcome doesn't match the actual outcome. So if you make a prediction about what's going to happen next, and what happens next is exactly that, there's no learning signal. You already know. You don't need to learn. You knew exactly what would happen next. Therefore, you're done learning. So it's when it doesn't match, there's a difference between your predicted outcome and the actual outcome that learning occurs. That's a really general principle, and exactly how that's instantiated in different brain systems differs. But that's a basic principle of learning, and it's the same principle that's used in machine learning. When you're teaching massive computers, you feed it information, the computer learns what's supposed to happen. This particular pattern is followed by this particular pattern. And the way it learns that is it's basically saying, did they match? No, change the weights. Next time, am I getting closer? Did the difference between predicted and actual get smaller? I'm on the right track. Or it got bigger, I'm on the wrong track, I gotta go and try something else. So that basic principle governs the brain and is at the core of a lot of the artificial intelligence stuff that's being done. So if what occurs is not what you thought would happen, that's an unpredictable. That's a surprise, in a sense. It's a teaching signal. So you need to update for next time. And then the other thing is that you can just have an unpredicted outcome out of the blue. So if you're learning, like you could be in a mode where you think, I'm going to learn. I'm going to do trial and error learning. I'm going to choose repeatedly from this pastry shop. And eventually, I'm going to discover, how good this pastry shop is and whether that particular donut is the best by repeatedly trying all the donuts until I find, the best one. And then having ascertained that's the best donut, one day I get a bad version of it, and that's a big surprise, and I'm going to change my whole perspective on donuts in that pastry shop. But you can also have completely unpredicted outcomes. You weren't expecting a donut. You're just walking along, and someone hands you a donut. That's a big surprise, and that will be a particularly engaging for the brain. That'll do more than drive learning. It really drives, orients you to this whole new experience. So there's different degrees of surprise. Okay, so that's why the brain learns. And I advance this with the mouse. I did that. Yep, okay, push harder. All right. So the question is, how does the brain learn? So memory is experience leaving its mark on the brain. And when you think about memory normally, you think about explicit memories, like what I just said in the last slide, wasn't that interesting? Or what you had for breakfast, wasn't that delicious? Or what you did last week or last year. But all the time your brain is being changed by experience. The experience of listening to me is slightly changing your brain. And if you're not listening to me and daydreaming instead, that's also slightly changing your brain. So your brain is never exactly the same. It may not be being changed in a very profound structural way, but it's being changed in at least slight electrical ways. And those electrical ways pile up repeatedly, it will change structurally as well. And that's basically how experience shapes your brain, and that's what memory is in general. There's different memory systems. There are several declarative memory systems that you have conscious access to. And then there's so-called non-declarative that are, if you want, unconscious, but are still examples of how the brain's been affected by experience. Let me give you some examples of what I mean. So episodic memory is what people usually think of. So when I ask you, what did you have for breakfast, or what did you learn about the person sitting next to you, and you can tell me about an episode, he introduced himself, he told me what he did, whatever, he was wearing a blue shirt. These are all features of an episode. That's what you usually think about memory. And then when you can't remember, he told me his name and I already forget, that's an episodic memory that's not as strong as it maybe should be. Working memory is a shorter version of that. That's information that you hold in mind just for a few seconds. If I give you a phone number, you hold it in mind until you've written it down. That's very brief. You don't hold it for long. It's very easily disrupted by distraction. It's a different brain system. I'll show you in a second. Semantic memory is knowledge about the world. So you probably know that Paris is the capital of France. But do you remember when you learned that information? Maybe we had a very impressive geography teacher and she banged on the map with the ruler. And that stands out in your mind still, all these decades later, how scared you felt. But probably not. Probably because you were exposed to the information that Paris is the capital of France many, many, many times. So gradually you just learn it as a fact, not as an episode. And that's a different kind of memory, and it's stored in different ways in the brain. And then there's autobiographical memory, your memory of your own life, which is also an interesting story that's kind of made up of a combination of these things. And just to give you, I guess, an example of what I mean by non-declarative memory, well, there's riding a bicycle, of course, so motor learning. So you practice, practice, practice. You match actual against predicted outcomes, and gradually your motor system gets good at a skill. And the same thing is, in fact, the identical system, more or less, is related to learning from rewards and punishments and feedback settings that govern a lot of our behavior. For example, why you have trouble stopping yourself from reaching for your cell phone because it might be rewarding. I usually scan my email to see if the Nobel Prize Committee is trying to get in touch. So that kind of learning can eventually become ingrained and turned into a habit, which is the stimulus generates the response, even if the response is not a goal. So the cell phone turns into that. I didn't want to check my email, but now that you've brought it up and I'm looking at it, I'm thinking about the Nobel Prize Committee. But even if I'm not thinking about them, there's still an automatic tendency to do that. And much of our actual behavior is in those automatic tendency modes. And that's good. It's efficient. But it's not good if you're trying to be flexible. So this is pertinent to later life behaviors in particular, because you have very long histories of these associations and habits that may be particularly difficult to set aside. Okay, so I'm going to get you involved here because it's post-lunch. So I'm going to have you do a little working memory demonstration just to see what you're up to. So I'm going to show you a series of single letters on the screen here in a second. You'll see a letter, and then it'll disappear. A new letter will appear, another letter will appear. Your job is to hold in mind the letters, and you're going to respond by banging on the table forcefully and quickly when you see a letter that you saw 2 letters previously. So I don't want you to respond if you saw the same letter 1 back, but if you saw it 2 back. Okay, so you're watching for the letter you saw 2 back, and you're going to hit the table, and we'll see how you're doing. Get ready. Okay, do you understand the task? So you're looking for the letter that you saw 2 back. Okay, here we go. Nice. Keep going. Keep going. pretty good. That's pretty good. So, can anyone give me that string of letters now? Oh, okay, you're bluffing. So even though that was a series of pieces of information, and you were holding them in mind, and I was asking you to update and refresh and keep that information protected from distraction because the letter in between was a distractor, right, for every comparison. Very difficult kind of working memory function. The fact that you did it at all, I'm very impressed by. I have a lot of trouble with this task myself, but it's a kind of memory. And temporarily, it was using your brain. You were using your brain to hold that information, but it's very temporary and on purpose. Who wants to have that string of letters in their head forever? It's not useful to you now, but in the moment, it was useful. And holding information in mind when it's no longer present in the environment is an extremely important, fundamental aspect of how the brain works. That's what lets you think away from what's around you and lets us project forward into the future, for decades and centuries. And imagine, and so on, is that we can work with information in mind without it being present in the environment. So this is really a fundamental part of complex cognition, the ability to hold information in mind and protect it from distraction, called working memory. And it relies on very specific parts of the brain, and they're not the same as the parts of the brain that are important for episodic memory, when you remember the episode of interacting with the person you sat next to when you first got here this morning. So there are different learning systems in the brain, and they rely on different brain circuits. And I'm just showing you an example. So the working memory task that you just did, that exact task, we had people with focal damage to the frontal lobes do to try to determine which parts of the frontal lobes are critical for that ability. There are reasons to think that frontal lobes are involved. And we study people with damage all over the frontal lobe, but we find only some of them have problem with that task, because it's a very specific kind of function and involves 2 bits of the frontal lobes, and they're shown. I don't know if I can use the mouse. Probably not. Or the pointer. They're shown in the top. There's 2 blue blobs there. Can I do? Oh, here we go. All right, I'll show you with the mouse. There's a bit of the medial frontal lobe. Damage here disrupts that task, and there's a bit of the left lateral frontal lobe. Damage there affects that task, but damage elsewhere in the frontal lobe doesn't bother. People with damage to the other parts of the frontal lobes are fine on this task. So it's very selective, the relationship between brain circuits and very specific behaviors when we isolate them like that in the lab. This is another example, I guess, of different kind of learning. These people were doing a task where they picked from decks of cards and they won or lost money. And they learned which deck was better. One of them was more winning. And then after a while, we changed the rules, and the other deck got better, and they had to change their behavior. That's kind of reward learning, flexible reward learning that's been studied a lot for various reasons. And people with damage to this underside of the frontal lobe, the orbital frontal cortex, they have problems with this task, but not with the task you just did. So just to illustrate for you, I guess, the fact that different circuits in the brain are involved in very different kinds of learning. And we can pull that out and understand it, even at this kind of big network level, never mind the kind of more details in the cellular level. All right, those are just some examples. I wanted to mention some of the stuff we work on. So what happens in this learning systems? They're all running at the same time. So it's not like you decide, I'm going to really remember this. It's kind of running in, and then depending on how important it is, you're going to hold on to it. Or not. And if you hold on to enough specific instances, it's going to turn from episodic to semantic. You're going to go from the teacher telling you about Paris, France, to the general knowledge of Paris, France, and those things are going to be stored or maintained in different parts of the brain as you go from episodes to semantic knowledge, from specific instances to general categories. You can think of it another way as going from data, like specific points of information, to knowledge, kind of a construction of holding together all these details in a more general way. And I guess you could make the argument that that is, let's say, a way of thinking about what is wisdom, is accumulating specific instances in a very rich way across a long experience and structuring that in a way that you can call on it when you need to. And another way of talking about that is to call it expertise. So what does it mean to be expert? So we're all experts at some things. So for example, we're all experts at face recognition. And I know Olivier claimed this morning that computers were better at it, but it's not really true. I don't think. Last time I checked. But anyway, if they're better, it must be a pretty close race, because for a long time it was quite challenging to teach computers to recognize facial emotions. It's very subtle, but we're very good at it, because we train on it all the time. We spend our whole lives watching very carefully other people around us, very important for our survival, especially when we're little, but even when we're big. To be able to detect that little look, right? When mom's looking at you, it's like, ooh, that's a very subtle perceptual signal, but kids are very good at picking it up. And if they don't, then they get a big teaching signal, right? So we're experts at recognizing faces and facial emotions, for example. But then we may have unique expertise. I'm a neurologist, so I'm supposedly expert at recognizing neurological diseases, because I see lots and lots and lots of them. And when I'm first learning that as a medical student, I have to learn it as kind of a set of facts. Like, this is the list of symptoms a person would have. But by the time you have developed expertise, you just look at the guy and say, I know what you have. And because you're an expert, you're able to pull out all the details without thinking necessarily about them explicitly and map them onto the category. That's Parkinson's disease, you say. And then you take the history and you show the medical student why it's Parkinson's disease, but you always knew that it was. That's expertise. And that's really powerful. It's very fast. It's a very efficient way to solve complex problems, and the brain's really good at generalizing from specific instances, building up to general cases. And that's, again, what artificial intelligence is also trying to do. Expertise has its downsides, though, because you have to no situation is identical. So you have to sort of ignore the details that you think aren't pertinent. So I'm making that snap diagnosis. This person might not have every single symptom that I see in the textbook, but I kind of put my finger over some of those parts so that it looks like what I'm expecting, and usually I'm right. Like, those little details are extraneous. But sometimes they're not, and this is actually a problem with experts, is that sometimes it's not quite the match, and we miss it because it's rare or it's close, and we discard a detail that was very important, it turned out. So it's called premature closure, and it's a problem that experts have to struggle with a bit, when to pursue further thinking and when to just call it. And that's true in any field. It's not special to medicine. So tendency to neglect new information. And also, I say the old ways are the best ways kind of affect a tendency to restrict your tactics to things that have worked for you before, which is learning. You learn, this works for me, this works. And that could be very useful, but it might prevent you from learning something new. So it's a trade-off between exploring new approaches and exploiting old ones. All right, so the aging brain, changing gears. So the trouble with studies of the aging brain is they've all been done by people who are 25, or maybe 30. So usually the focus is on the this is young people in their 20s. This is their excellent performance on a bunch of tasks, including that working memory stuff I was talking about. They're all doing really well up here. And then, on these tasks that are just so vital, over time, people get, worse. I mean, it's just plus or minus one standard deviation. Don't panic here. But there's decline in many cognitive functions, working memory, speed of processing, and others. But then, on the other hand, there's some tasks that people get better at over time. And those are things like vocabulary, world knowledge, and so on, this accumulation of information, and if you want, wisdom that's measured in the lab with those kinds of things. So some things are stable or improve over the lifespan, and some things worsen. And the question is, which is more important? And if you ask a 21-year-old, they'll say this stuff, and if you ask someone in their 90s, they'll say this stuff. Fine. Some brain regions are more vulnerable to aging changes than others. And the speed of change across the lifespan is different. And the main thing I wanted to say about this is that this is on average, and individuals really vary. And most of what we know about this is not learned by studying people who sign up for the study in their 20s and are scanned every 5 years for the rest of their lives. We don't have time. No one's going to fund us for 50 years. So we just call everyone in and line them up on this graph. So it's actually quite difficult to know for sure whether what we think we know about changes with time, especially in brain structure, are actually related to just with age, that if you followed one person over time, they would definitely show these patterns, or they're kind of cohort effects, because if I do a study today, people in their 90s were born 90 years ago. That's different from people in their 50s. They were born 50 years ago. There are a lot of differences about their life experience that might be as relevant or partly relevant to their brain state now besides their age. So we have mostly cross-sectional data, and we're starting to get longitudinal data in the same people over time, but it's quite restricted to just a few years of follow-up. So we don't know yet, but in general, there's a tendency for some parts of the brain to get smaller with age. And as I said, not everyone shows that effect. So this is showing the volume of the hippocampus, a famous memory important brain structure that is sensitive to age effects. It declines in size with age. This is the same people studied 5 years apart, and their average volume of their hippocampus. And you see two lines, one that's pretty stable, and the other with the dotted line there was showing decline over time. And those are two groups of people who vary in life experience, so-called life experience quotient. So the richness of their lives, their educational levels, and other aspects of their engagement, and whether or not they belong to MCLL. I'm not sure that was specifically mentioned. But that's the idea that some people are more vulnerable than others to these changes with age. Okay, so that brings me to the topic of plasticity, which means a lot of things, in fact. So neuroscientists are very interested in the idea of the brain healing itself or changing adaptively after injury. Literally, the axons, regrowing, new brain cells being generated. And that's, for sure, that's going on. Probably not as much as we might think. I mean, major brain injuries, that's not an easy way to solve, to recover. More likely the brain has, I mentioned there are many memory systems, they're all running at once. Well, if one of them's not working very well, you'll use another. The other one will start to dominate it. It may have its own strengths and weaknesses, but it's there to help you out. So if your working memory isn't so good, well, maybe you'll be able to remember it in another way. You'll like explicitly say, I'm going to have to repeat that guy's name 10 times, so if I can't just let it go in and out again, it'll be gone. My working memory's weak. So there's ways to use other systems, and the brain typically finds those. But more to the point, and that's what we were hearing about earlier, and which I think we should keep talking about, is the person finds workarounds to carry out the function. So if your memory is bad, well, write it down. Right? What's the big deal? That's obviously a kind of plasticity. It's very effective. It's not maybe what you were hoping for, with the brain growing new axons, but it works, and I would recommend it. And then the other thing is the person's environment adjusting to take the pressure off that particular brain function, and that works really well too. So we heard about that this morning. I'm going to skip this. All right. So what factors protect your brain health over time? So what's good for your heart is good for your brain, it turns out. So in midlife or earlier, if you have lower rates of cardiovascular risk factors, your likelihood of developing cognitive impairment or dementia with old age is lower. So if you smoke, I suggest you quit. If you have high blood pressure, I suggest you treat it. Try not to get diabetes, and if you have it, treat it. Cholesterol and healthy body weight, these are important. And they're important, of course, for our general health, but they're specifically important for the brain. The brain uses 20% of the body's cardiac output. It really needs a good supply of energy, blood flow, and the blood vessels are very tightly related to the functions of the other cells in the brain. So it's not just the brain bringing some blood in. There's more to it than that. There's a lot of interaction between the vascular system and the brain, and we don't understand all of it, but it's clearly important, and some of these things are preventable or modifiable, so they should be prevented and modified. The other thing that's maybe more important, and I'll show you why I say that, is that what's good for your mind is good for your brain. So high educational attainment is definitely good for your brain. And so is strong social relationships and having high social status. So if you can arrange that, I recommend that too. Physical activity, engagement and meaningful activities, and relatedly, I guess, a sense of control. So these are not necessarily unrelated to each other, but these kinds of things are good for your brain. And what's more important, I guess? Is it more important to worry about your cholesterol, or whether you should be eating more legumes, or to deal with this stuff? So we know a little bit about that, actually. So this one study that's fairly recent, this isn't my work, but I think it's very interesting and informative. This is older people, healthy older people in Manhattan, in fact, looking at the effects, at the likelihood of cognitive decline over several years in relation to how much education, formal education they have, and other factors. And what you see here is cognitive change on cognitive testing, starting, when they were first entered into the study over up to 9 years, the trajectory. So there's a general sense that things are tilting downwards a bit on cognitive performance. But where you start really depends on how much education you had. So if you had no years of formal education, you're way lower than someone who has 16 years of formal education to start with. Not a big shock, but there it is. Maybe what's more important is if you look at the decline over time, the person with 16 years of education has a much flatter curve than this person with no formal education. They're dropping faster. So they started lower and they're dropping faster because of early education. In early childhood, we're talking about primary school. And if you look at what's driving this, in the people who have low education, it's directly affecting their cognitive change. They're likely to decline the lack of education below in childhood. Now, in their 70s and 80s, is affecting their likelihood of cognitive change. In people with more than 8 years of education, it's going through income. So they're doing well out here, but their education isn't directly the cause. It's going through all the things that come with higher income, better health care, social status, etc. So to me, this is sort of the social justice argument that education, investing in education in childhood is a public health issue decades later. And then the last thing I'm just going to mention is that social experience changes the brain. And this is from work in my lab where we're looking at social network size of healthy older people. So the bigger your social network, the more you use your social brain. And we can see that. We can see that there's differences in specific parts of the thickness of the cortex that relate to social behavior, and that the white matter cables that connect those parts are stronger for people with higher social networks. And there's also work, not by us, but we're just about to start into this stuff, looking at social inclusion and exclusion and how that affects the brain. And that is where my last message here. This is the effect size of different factors in terms of mortality now. I'm not talking about the brain anymore, just surviving. And the top three, which you can't see because they're probably too small, these are big effects. And they have to do with social relationships, social support, social integration. The more of that you have, the less likely you are to be dropping dead. And where's smoking? Smoking's here, if you smoke or don't smoke. Okay, and where's fat versus thin? Down here, it's a much smaller effect. Air pollution, blood pressure treatment. So medicine spends a lot of time worrying about this, but this is where the action is. And this is something that society needs to take on, and I think is very relevant to aging and chronic disease and marginalized populations. And this is the take-home message about what you can do today to make your brain work better in case you didn't quit smoking 30 years ago. Okay, maybe I'll stop there, because I'm out of time, and take questions if there's the opportunity. Thanks a lot.
Doctor, you talked about the prominence of education as a factor in protecting the brain and years of education. Does that mean learning?
Well,
is that what that means?
Well, of course, it can be hard to know what goes with. The really striking effects are for people who have very little education. That's, like, if you're thinking about formal education, I mean, you're talking about people who have less than primary school, than completing primary school. They're the ones who carry the big brunt of age-related cognitive decline and dementia. I see that in my own clinic. Of course, I see cognitive impairment, dementia, and so on, and it affects people across all social strata, but I have a lot more patients with grade 4 educations who worked in the textile factories than I have university professors. It's the case that the very low educated really have very little reserve to draw on, and they're more likely to show cognitive decline, more rapid cognitive decline, and dementia than people with higher education. Why? The mechanisms, it's not entirely clear, but it's likely to relate to these social determinants and perhaps also to many other factors, healthier environments, less stress, more resources in all kinds of ways. That's a very complicated thing to chart over a lifespan. But it does suggest that if you're worried about, the aging dementia epidemic as a policymaker, you should have worried about that 60 years ago and kept people in school, and we shouldn't keep making that mistake. America, are you listening? Yes.
We've heard several times today about the virtues of staying in your own home when you're older. And I have an automatic reaction to that, living in a very good seniors residence, that's wrong.
Mm-hmm.
That basically the people I know who are 85 to 95, who stay in their own homes, are restricted in the number of people they come in contact with, and most of their friends are dead, and life is just very hard. And if you live in a place like the Manoir Westmount, you live in a perfect environment, which is kind of like university was,
Right.
with all the things you don't want to do looked after, all kinds of interesting people to interact with, and you stay much healthier.
So I totally agree with you that it's more important to think about having people engaged and in lots of social contact. The brain is really made mainly, as far as I'm concerned, for social behaviors, and it's just borrowed for other things like playing chess or whatever. So I really think that that's one of the biggest drivers of brain function, and frankly, obviously, extremely important for quality of life. So even if it didn't drive brain function, I'd be a fan. And that the idea of staying in your own home, of course, I understand where it comes from, but I completely agree with you. I'm forever trying to convince some of my patients that they would be happier, more engaged, and more protected from further decline in settings where they had less stress about burning the house down and more social interaction. Absolutely. And maybe that's just a place to say that all these factors that influence the development of a neurological disease or a mental health condition, like engagement and status and education, they don't just disappear once you have the disease. They keep protecting you from decline, even if you have Alzheimer's disease. So there's work on this, not my own work, but my experience in the clinic is really clear that the people who are in tight-knit families, or they're in they have the resources to be in a really good assisted living facility, they have social support, and they do better than people who may have many resources, but families all in Toronto and they're kind of parked, that they do worse. And maybe it's no surprise. But the mechanisms, the detailed mechanisms of that from the brain point of view are fascinating. We're working on it. I'm really interested in that these days. And the size of the impact of it is large. We should be paying more attention to that in neuroscience, I think. Social media? Yes. Right.
I'll repeat the question. Well, I'm curious to know about if you've done any research on the impact of social media on the importance of social relationships in maintaining a healthy brain.
Right. Really good question again. So I was struck that Kathleen was focused so much on the importance of having a physical space to meet face-to-face with people. I'm like, what kind of a young generation person is this? You're never going to get all your 1,000 Facebook friends in that room. Is she still here? I'm giving her a hard time in her absence. I really enjoyed your talk. But the fact is that even in the age of social media, the social network that probably really matters is the old-fashioned one, where you actually know the people and see them in some regular way. And the size of that network hasn't changed over time, despite the fact that the virtual social networks, your thousands and thousands of followers on Twitter or whatever, have expanded. Those people, who have big networks like that, and those people who have small networks like that, their actual social network, defined in old-fashioned terms, is about the same size that most people can manage, 50, 60 people-ish. And probably it's the case that that's what's mainly driving all these brain systems that we're interested in studying, but I don't know that. We're working on that to some degree. I think we're going to find that I guess that's an interesting point for thinking about online interaction or social media-driven interaction for older people, even if we can get them on their computers. I am not so sure that's where the main value added is if what we're talking about is interaction, integration, and certainly not alone. I don't think just that is going to bring a whole lot, personally, but that's speculation. No evidence base. Okay, the speculation part, yeah. Okay, yeah.
All right, I'll just bring the focus back to young people for a quick second. Your last slide says that addressing mental health challenges is important to protect brain health right now. My question was, how big is the impact of mental health issues? And a second part would be, is there a difference between early intervention versus like late intervention after like a long period of not being, because mental health is becoming a crisis across Canadian university campuses all over. I think some of the speakers mentioned it earlier as well, but.
Yeah, I mean, I don't know if mental health is becoming a crisis. I think maybe people are just talking about it more, but which is for the good. I don't, off the top of my head, know a literature, maybe there isn't even one, a literature about the kind of, let's say, anxiety and stress sorts of things that are preoccupation on campus these days in terms of decades of experience later. Of course, every generation's faced anxiety and stress, but it's difficult to compare across them. Kind of the context of these things changes over time. I was mostly talking about here the fact that if a person right now has these issues, their cognitive function is going to be affected. And these are treatable, addressable problems that can be addressed. And people are able to focus better if they're not feeling chronically stressed and anxious, and they're going to perform better cognitively. Now, as it were. So that was more what I was talking about here. Whether, I think some of that information, the work on, let's say, the social determinants of brain health in the long run would argue that it's chronic stress throughout life, and maybe especially in crucial early parts of your life, that particularly mark the brain for trouble later. But a lot of that is a bit of a leap from the data, but it seems like a plausible leap. Yeah.
So there is hope for our young people.
Well, I think the people who are at McGill, there's a lot of hope for them. I mean, I don't want to minimize their situation, but the kinds of chronic stress and deprivation, and those are the kinds of things you're seeing in refugee camps, and like that marks the brain. Your midterm? So I don't want to minimize it really, but I think maybe that's one of the things we could help with, right? Is context and help people sort of step back a little bit. These are things that can be relatively easily addressed because there are many resources available usually to these people in general. But of course we need to take them seriously, for sure.
You have to stop.
Yeah.
I won't make you luncheon speaker next time.
Okay.
Thank you. My question is similar. I just wanted to know about depression and how depression fits into your statistics.
Here we are. There you are. It's one of the, depression has, it's in the brain. And it's, so it can be, depressive symptoms can be a feature that goes with cognitive decline. And depression sort of independently can cause some degree of difficulty, especially with the kinds of tasks that I had you doing earlier, working memory, attention, those kinds of processing tasks that are really fundamental. It's temporary. That's why treating it can help people perform better. So it's pertinent, and depression is not rare in older people, and it's addressable. Whereas Alzheimer's disease, we don't really have treatments for, really, not very effective ones. So these are the things I'm trying to focus on in my clinic first, to deal with things we could fix, if we can.